Let's have a quick go at proving one of Newton's three laws of motion, the second law. This law states that if a resultant force acts on an object, the object will be accelerated in the direction of the force, and this acceleration will be directly proportional to the size of the force. The law is generally summarized as F equals ma. Force and acceleration are directly proportional, so as the force goes up, so does the acceleration by the same factor. That's for a certain object, and mass doesn't change. What we're going to do is keep the force constant. Mass and acceleration are inversely proportional, so as the mass goes up, which it will be, acceleration will decrease. By keeping the force constant and knowing the mass, we can rearrange the equation to solve for acceleration. This will be the theoretical acceleration, i.e. theory tells us the acceleration will be this. Then we go ahead and do a prac to find out what the actual acceleration is in real life. If Newton's law is correct, and spoiler alert, it is, then the experimental acceleration we get through the prac should match the theoretical acceleration. To determine the experimental acceleration, we'll use this kinematics equation. It looks tricky at first glance, but really it isn't too bad. A and t represent acceleration and time, respectively. That much is clear. But s and u? Well, s is just displacement, essentially the distance in a straight line. We're going to use a dynamic trolley for the prac, so s is the distance the trolley moves. As for u, that's initial velocity. The good news is the trolley is going to start at rest, so initial velocity is 0. That means we have 0 times time, which will be 0 because that's how maths works. This means we can remove ut from the equation and just have this, s equals half at squared. Then we can rearrange that to solve for the experimental acceleration, which is a equals 2s over t squared. So, now we know how to find acceleration, both theoretical and experimental. Let's take a look at the actual prac. This is what we need. We have a pulley clamped to the edge of the bench, the base of a retort stand to stop the trolley itself with a length of string attached, a stopwatch, a variety of masses, and a meter ruler. We set up a mass carrier with slotted masses hanging via string over the pulley. I used 9 50-gram slotted masses, plus the mass carrier itself is another 50 grams, so that's 500 grams, or half a kilogram, of mass ready to fall. This is what will supply the constant force, the force of gravity acting on this mass. Let's take a look. Here is our setup. We have a half kilogram hanging mass from the string over the pulley to this trolley. We measure the distance to our starting gate of the trolley. We're going to release the trolley from here, and the distance is, 82-ish centimeters, 82.5 centimeters. Of course, we're not going to call it 82.5, we're going to call it 0.825 because we work in meters. We're going to time our stopwatch, working in seconds. We're going to time how long the trolley takes to travel the distance. It will be accelerated due to the force of gravity pulling this mass down. So the force will remain constant because we're keeping that mass the same each time. We're not going to be changing it. Okay, so the prac was run 3 times with each trial timed. Here's the result from the first trial, 0.59 seconds. I started the stopwatch when I released the trolley and stopped it when it crashed into the retort stand base, but there's always error involved. Running 3 trials means we can take the average to try to eliminate some human error. The first 3 trials were run with just the trolley, which had a mass of 470.9 grams, or 0.4709 kilograms, since we're going to work in kilograms. I then increased the mass by half a kilogram and ran the prac another 3 times. Then again with a kilogram on the trolley, and 1.5 kilogram, 2 kilograms, and 2.5 kilograms. Here's what rough results look like. These are then put into a table like this one. The mass of the trolley doesn't change, but the total mass does, as I kept piling on an extra half kilogram. The force applied by the hanging mass, which is what accelerated the trolley, was the force of gravity acting on that hanging mass. Gravity on Earth is 9.81 newtons per kilogram. Well, I had half a kilogram hanging mass. So the force accelerating this mass towards the ground, and therefore accelerating the trolley, was 4.905 newtons. The distance the trolley travelled was 0.825 meters. Putting the rough results into the table looks like this, with the averages for each mass calculated. Using these average times and the distance the trolley travelled, we can determine the experimental acceleration for each mass. I find the easiest way to do this is put the data in a spreadsheet like Excel or Google Sheets. Then we can input a formula and apply it to each row. To do this, we use the equals symbol to start a formula, input what we want. In this case, it was 2 times s, then that is divided by t squared. Hit enter on the keyboard and the answer is put into this cell. Now by highlighting the cell with the answer, we can click the corner and drag down. This will apply the same formula to the cells below. In this way, we only need to do it once and let the computer do the repeated maths. Then we highlight the answers and choose the number of decimal places to round to and copy the answers back into the results table. The theoretical acceleration is worked out in the same manner. We have the force applied by the hanging mass, the total mass of the trolley system, and using F equals ma, rearranged as A equals F over m, we can calculate the theoretical acceleration. It's back to the spreadsheet to get the answers, and these are put into the official table. Now, to the crux of the whole thing. We plot a graph of both accelerations, experimental and theoretical, against total mass of the trolley system. The easiest way, once again, is to use a spreadsheet. I have a video on how to do just that. Anywho, the graph comes out like this. The orange results are the experimental accelerations and the blue are the theoretical. I added exponential trend lines to each so we can see the general trend of each plot. And what do we notice? Well, they both show a curve, but A, not quite the same curve, and B, the curve of theoretical acceleration is distinctly higher than that of experimental acceleration. So what's going on here? If Newton was so clever, and he was, why don't they match up exactly? Well, in the calculation of theoretical acceleration, what was considered? Just the force applied and the mass. That's it. But in the real world, we have retarding forces to contend with, such as friction. That's the thing with physics. Frictional forces are often ignored, but in the real world, they can play quite a role, both in terms of static friction and kinetic friction. I would argue that within the bounds of high school equipment, and with just one person doing the prac in a rushed manner, I did it in less than half an hour during break, and when factoring in friction forces, the two curves are actually in agreement. If I'd had more time, I could have looked at running the prac a greater number of times. 6 results is not ideal. I would have preferred at least 8. And perhaps run the entire prac again with a different hanging mass. And instead of using an old beat-up stopwatch, a light gate could have been used, which would electronically measure the time for the trolley to cover the distance. Now these are all modifications that could be made to the prac should I run it again. But in the meantime, I'm going to say that within the bounds of what I had to work with and time constraints, I just proved Newton's second law of motion. Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.